Use the intermediate value theorem, the IVT, to prove that f of x equals x to the power 15 plus 1 over 1 plus sine squared x plus r plus 1 squared has at least one zero on the interval from -1 to 1 for any real r. So r is a constant and it's a real number, but it has to be true for any real r. We're going to use the intermediate value theorem. Then that suggests that the function is continuous on this interval, because if it wasn't, we wouldn't be able to use it. So really we need to show that that's the case before we do anything else. So once we've done that, we'll look at the endpoints, but let's go into it. So f of x equals x to the power 15 plus 1 over 1 plus sine squared x plus r plus 1 squared. So the first thing you would do, when alarm bells would start ringing, when you see that there's a division in the function. So that means, remember, if ever you divide by 0, you have an undefined area, a discontinuity. So you need to think, could this denominator ever be 0? So you need to pick the terms apart. Well, you know that 1's always greater than 0. So if we take the sine squared x, well, the fact that we're squaring it, sine x can obviously be negative or positive, but once you then take that and square it, well, that is going to be greater than or equal to 0 for x, all real x. R plus 1 squared, well, r we don't know what it is. But once we add 1 to it and then squared, squaring being the key, it's not going to be negative. We've been told r is real. So it means that when you square it, or when you add 1 to it and then you square it, it must be greater than or equal to 0. R plus 1 squared also must be greater than or equal to 0 for all real r. So that means 1 plus sine squared x plus r plus 1 squared must be greater than or equal to 1 for all real x and all real r. Okay, so that means that this function is continuous everywhere. There's no issue with the x to the power 15, and the fact that this denominator can never be 0 means that when we divide 1 by it, we will always get a number. Right, so f of x is continuous. It's continuous everywhere, but we're going to say it's definitely continuous on this interval. Okay, so once we know that, that means that we can potentially apply the intermediate value theorem. Now, to apply the intermediate value theorem to find zeros, you need to show that the value at one end, as in f of -1, has a different sign to f of 1. Right? We need to show. Now, the intermediate value theorem works for, it applies to closed intervals, but the open interval shouldn't be an issue unless we have a problem on the endpoints, but I'm sure it'll be absolutely fine. Let's think about f of 1. So we'll start with f of 1. F of 1 equals, well, it equals 1 to the power 15, which is just going to be 1, plus 1 over 1 plus sine squared 1 plus r plus 1 squared. Okay, so we can't do a lot about the 1 to the power 15, it's just 1, not going to change. Neither is this one, sine squared 1, we will work it out, but the point is it's just a number. The bit that is an issue is this r plus 1 squared. Now we need to think what value of this would make, we're trying to bound f of 1 and show that whatever the bounds are, it gives the same sign. Right, so you think what value of r would maximize this f of 1, what value of r would minimize it? So if you want to find the biggest possible value of this whole thing, well, because we're adding this fraction part, you want this fraction to be as big as possible. The way you make a fraction as big as possible is you can make the denominator as big as possible, sorry, the numerator as big as possible, but we can't do anything with that. Or you can make the denominator as small as possible. So to maximize this, how could we make this denominator as small as possible? So we want this term to be as small as possible. Well, it can't be negative, so the smallest it can be is when r is -1. So when r equals -1, f of 1 equals, well, let's just put it in. It's going to be 1 plus 1 over 1 plus sine squared 1, which I think on a calculator better write sine 1 and then square it, squared, plus, well, it's plus r plus 1 squared, but we said r was -1, so it's actually just that. Okay, so that gives us a value of 1.585. Okay, so that's that's when we made this as big as possible. So if we make this as small as possible, well, that is going to be when this fraction here is as small as possible. It's the only thing we can actually change, right? So to make this as small as possible, we need to make the denominator as big as possible. So really, that's when r gets really big. So when we let r approach infinity, well, the denominator is going to approach infinity. So r plus 1 squared is also going to approach infinity, which is going, I mean, the 1 and the sine squared 1 don't do anything. It's basically a constant plus infinity, and then we divide 1 by that. This whole fraction is going to approach 0, right? So 1 over sine squared 1, I've lost the 1 plus sine squared 1 plus r plus 1 squared, well, that is going to approach 0, right? So f of 1 is going to get very, very close to 1 to the power 15, which is 1, right? So that is telling us now that f of 1, we can say, well, it's going to be less than or equal to this 1.585, and it's going to be sort of greater than 1. But either way, it's definitely positive. So now we need to take a similar approach to f of -1. F of -1, let's have a look at that. Well, it's -1 to the power 15, which will be -1, plus, well, actually, we can do a few of the shocks. I suppose the sine squared -1 will change. Well, let's write it down. 1 over 1 plus sine squared -1 plus r plus 1 squared. So still, to make this thing the biggest possible, we're going to still make this bit equal to 0. We still want to divide by as little as possible. So when r equals -1, f of -1 equals, let's just put it in. So it's going to be -1 to the power 15, we said, was -1 plus 1 over, and it's 1 plus sine of -1, and then we square that, and it's plus 0. So let's have a look at that. That gives us an answer of minus 0.4145. Minus 0.4145. Okay, so it's negative. It's a good sign. We still keep the same value of r, so when we let r approach something very, very large, when r approaches infinity, f of -1, well, that's going to get very close to, remember, this is just Small constant plus gigantic number. 1 divided by the gigantic number approaches 0, which means that this whole thing is going to approach minus 1 to the power 15, which is minus 1. Okay, so that means f of minus 1 is bounded between, well, it's got a low point that it doesn't quite get to of minus 1, so it's greater than minus 1, not much greater, and then it can be less than or equal to minus 0.4145. But either way, we have shown that f of minus 1 for any value of r is negative, and f of 1 for any value of r is positive. So we've done all that, and we have shown conclusively that f of minus 1, we have shown that that is negative. So that means that is less than 0. We have also shown that f of 1 is greater than 0. So that is true. So since that is true, that's part of the story, right? And the other part, remember, is this continuous bit. And f of x is continuous on this interval. Okay, so since both of those things are true, there must exist, there exists a c which is in this interval such that f of c equals 0. So there is a 0, and the reason why we know this is because of the intermediate value theorem. So there is a 0. And the original question actually asked us about an open interval, where there must be a 0 on that as well, because we know that the only difference between the open interval and the closed interval is that the open interval just excludes these endpoints, and seeing as neither of them were 0 anyway, there must be a 0 in the middle somewhere, at least one 0. So there's also a 0 on this one, which is what the question asked about in the first place. Right, part B is a lot easier than it looks. So let R, a real number, let R be a real number. R is greater than 0, and let it be any constant, right? Can the intermediate value theorem be used to prove the existence of a 0 in the open interval from minus 1 to 1 of g of x equals, this is b, I'm just going to write down g of x equals rx to the power 17 plus 1 over 5x. So we're looking at g of x, and we're interested in the interval from minus 1 to 1, and it's open. Hopefully you can look at that and realize that we have a problem immediately. Remember, the intermediate value theorem demands to find zeros, you need to show a sign change between the two endpoints, but you also need the function to be continuous across the whole of that interval, and it clearly isn't, because if x was 0, this function is undefined, right? So g of x has a discontinuity at x equals 0, and so the IVT cannot be used. To find a 0 in the interval. Okay, and I don't really think we need to write anything else than that. There's really nothing else. You can't apply the intermediate value theorem if you don't have a continuous interval on which you're applying it on. So you don't have to worry about the R, thinking about values or anything like that. The question was, can we apply the intermediate value theorem? The answer is no.